Class, today we're going to talk about coordinate systems, which are basically different schemes that can be used to encode locations in space. We're also going to talk about how data encoded in one coordinate system can be transformed into another coordinate system. This is often incredibly useful because, as we'll see in this lecture, some problems are much easier to solve if, for instance, we translate data from Cartesian coordinates to polar coordinates. Alright, so let's dive into coordinate systems. A coordinate system is a mathematical system that allows you to define points or other shapes in a geometric space using ordered sets of numbers referred to as coordinates. Using defined coordinate systems allows geometric problems to be easily translated into mathematical problems. There are many different coordinate systems because often specific questions will be much easier to phrase if translated into a specific coordinate system that is most applicable to that problem. That statement might not make a ton of sense to you at the moment, but the examples I'll use throughout this lecture will help you develop an intuition for why you might want to use different coordinate systems. Specific coordinate systems can be defined in 1 dimension, 2 dimensions, 3 dimensions, or even more dimensions. An example of a one-dimensional coordinate system is the number line. Any real number can be used to define a specific point to the left or to the right on the number line. One-dimensional coordinate systems are incredibly uninteresting, however, so we're not going to talk about them any further. Another example of a coordinate system is the Cartesian coordinate system. There can be Cartesian coordinate systems in 2 dimensions or in 3 dimensions. In 2 dimensions, the Cartesian coordinate is defining points on a plane, with the x dimension defining left and right and the y dimension defining up and down. In 3 dimensions, the Cartesian coordinate system defines points in 3-dimensional space, with the third z-coordinate typically implying a direction that you might think of as coming up and out of the screen or page. Another commonly used coordinate system is spherical coordinates. Just like the 3-dimensional Cartesian coordinate system, spherical coordinates can be used to define any point in 3-dimensional space. However, instead of defining space using x, y, and z coordinates, the spherical coordinate system defines all points in space based on 2 angles, which are usually referred to as theta and phi, and a radius that determines how far the point is from the origin or the middle of the coordinate system. Alright, our next major topic is transformation of coordinate systems. Coordinate transformations allow us to move from one coordinate system to another system. For instance, let's say we were working in polar coordinates. Polar coordinates are a coordinate system for defining points in 2 dimensions. The polar coordinate system defines points in 2 dimensions using an angle and a radius from the origin. For instance, the point 1, 30 degrees is at a radius of 1 and an angle of 30 degrees. The point 3, 150 degrees would be at a radius of 3 and an angle of 150 degrees. Hopefully you can see how this could be used to define any point in space. The polar coordinate system can be very useful for working with shapes like circles or spirals. It can also be useful if you're doing something like, for instance, making magnetic measurements around the South Pole. But what if your friend was making measurements using the polar coordinate system and you needed to convert them into the Cartesian coordinate system? Like, let's say your friend gave you 2 points defined by a radius and an angle, and you needed to figure out how far apart they are. Well, remembering back to our trigonometry lecture, we can define a triangle for this point. The hypotenuse of this triangle will be equal to the radius, while the bottom side will be equal to r times the cosine of theta, and the right side will be equal to r times the sine of theta. Hopefully, by looking at that, you can see how we can relate our Cartesian coordinate system to the polar coordinate system. We can write that x equals r times the cosine of theta, and y equals r times the sine of theta. We can thus see that these equations can translate the polar coordinate system into the Cartesian coordinate system. We could also write a set of equations that translate back from the Cartesian coordinate system into the polar coordinate system. Calculating r from x and y is pretty easy. It is simply the square root of x squared plus y squared. However, calculating theta is a bit more complex. If you remember our trigonometry toolbox, you'll remember that the tangent of an angle is equal to the opposite side divided by the adjacent side. Taking the inverse tangent can thus get us part of the way to getting the angle from our xy coordinates, but it's a bit more complex. Because remember, the trigonometric functions are cyclic, so they don't have true inverses. For instance, the inverse tangent function only gives you values between negative 90 degrees and 90 degrees. So what we're going to do is define a new function. We'll call it f of x comma y for now, and we'll state that f of x comma y is equal to the regular inverse tangent if x is greater than 0. However, if x is less than 0, we'll state that f of x comma y is equal to the inverse tangent plus 180 degrees if y is greater than 0, and we'll set f of x comma y equal to the inverse tangent minus 180 degrees if y is less than 0. This function thus nicely maps our angles all the way around the circle. Alright, we've got these nice equations that translate polar coordinates into Cartesian coordinates, and Cartesian coordinates into polar coordinates. Why might we actually want to do this? Well, we all live in Florida, and recent history has taught us that here in Florida we need to worry about hurricanes, and warmer surface ocean temperatures associated with climate change might make hurricanes even more devastating in the future. So we might decide to study hurricanes, those big whirling, swirling cyclones that are fueled by latent heat transfer as moist air condenses into rain. The eye of the hurricane is a region of very low atmospheric pressure in the center of the hurricane with high-speed winds rotating around it. Hurricane strength is related to how strong that low-pressure zone in the hurricane is. So maybe we want to investigate the relationships between wind speed and atmospheric pressure in the hurricane. But this is a really complex problem. Even if we forget about the temporal evolution of hurricanes and focus on just one snapshot in time, hurricanes can have really complex structures. Let's say we used some satellite imagery and got an estimate of what the wind speed and air pressure were at different locations within the hurricane. Our satellite is going to see the world in Cartesian coordinates, so that's what our data is in. We've basically got these pictures of wind speed on the top and air pressure on the bottom, but how can we start to make sense of this? Remember, our satellite is going to be giving us multiple images of the hurricane every day, and we want to compare all of those images and then compare to other hurricanes as well. That's a lot of data to keep track of. Well, one thing we could do is just ask, what's the maximum wind speed in the hurricane and what's the minimum air pressure? We could then get some data on just those two things and then relate maximum wind speed to minimum air pressure for a bunch of hurricanes. But you know what? That's not the most useful thing in the world. Because if I'm sitting here in Tallahassee, it's not just the maximum wind speed that I care about. I also care about the wind speed in other parts of the hurricane, since those other parts of the hurricane might be the part that hits my house. The wind speed in those other places might also not be related only to the minimum air pressure. They might depend in part on how wide the hurricane is and how large the zone of low air pressure is. So we may want to actually try plotting comparisons of wind speed and air pressure. But where should we start? Let's say we just drew a horizontal line through the hurricane and plotted the wind speed and the air pressure along that line. If we draw our line through the upper limb of the hurricane and then graph both wind speed and air pressure as a function of distance east-west through the hurricane, these are the curves we get. We see that wind speed peaks towards the middle of our line, and we see that air pressure drops towards the middle of our line. So we can see that there will be a nice inverse relationship between air pressure and wind speed. When air pressure is low, wind speed is high. But that was just one line through our hurricane. What if we draw our line a bit further to the south? If we instead drew our line where you see the new blue line in the figure and then graph the exact same things, this is what we would get. We now see a very different pattern. The air pressure pattern looks pretty much the same, but the wind speed pattern looks very different because now our line is crossing almost through the eye of the hurricane. We would thus see a different pattern in our air pressure to wind speed pattern. This is kind of problematic because it means that if we really want to understand the wind pressure relationships, we're going to have to look at everything in 2 dimensions, which is way more complex. Unless we try something smart and convert everything to polar coordinates. If we convert to polar coordinates and set our origin as the middle of the hurricane, then it really doesn't matter what angle we choose. Since our hurricane is pretty much circular, wind speed and air pressure are just a simple function of how far from the center of the hurricane you are. Thus, in spherical coordinates, we could graph wind speed and air pressure as a function of distance from the center of the hurricane, or in the language of our polar coordinates, we graph them as a function of the radius. When we graph things as a function of the radius in polar coordinates, instead of x or y in Cartesian coordinates, we now find a generalizable pattern. Wind speed increases rapidly from the center of the hurricane, then slowly declines after reaching a maximum. Air pressure, by contrast, increases slowly for just the first few kilometers, then starts to increase rapidly before leveling off. The really nice thing about polar coordinates is that we'll get the same relationship no matter what angle we pick. We could thus produce a whole bunch of these plots for different hurricanes and use them to diagnose patterns in the relationships between wind speed and air pressure as a function of distance from the center of the hurricane. This whole process is much easier working in polar coordinates than in Cartesian coordinates. Let's talk about another example. Imagine that you're working for the Park Service and they've asked you to make a new map for a small state park. So your first step is to figure out the boundaries of the park and plot them. Next, you go onto the USGS website and you download topographic data for the region that was provided as a vector art file for Graphical Information Systems, or GIS. Vector art files store XY or latitude-longitude vectors that basically tell you where to plot lines on a graph. So you can plot these vectors and get a topographic map for the park. Your topographic map shows you some of the key features of the park. The park is oriented along a river that cuts through a canyon. The canyon is clearly steeper on the northwest side of the park than it is on the southeast edge. Next, you take out a GPS, turn it on, and log positions while you drive through the roads in the park. This allows you to get a file with all of the latitudes and longitude values for the roads in the park. So you can add those to your map. Your next step is to take your GPS and walk all the trails in the park so you can add all of the hiking trails onto your map. And finally, you put in some nice little images to show where the visitor center and the campgrounds are. Alright, so you've produced this nice little map that can go on the park website. But your bosses also want something that they can print out and give to tourists to take around in the park. And if you look at your map, you can see that the park is not oriented nicely north-south. Instead, it's tilted, since it centers along the river running through the park. So if you want to maximize the size that you can print your map on a piece of paper and not have a lot of wasted space, you'll actually need to rotate it. And for that, we can use transformation of coordinate systems. But in this case, we're not going to transform our data into polar coordinates. Instead, we're going to define a new coordinate system just for our park. Let's define our new coordinate system so that the origin is at the southernmost corner of our park and the axes extend along the two edges of the park. Instead of calling these axes x and y, let's call them A and U for across river and upriver. We thus want to figure out a transformation that will take our latitude and longitude data and transform it into our new AU coordinate system. So what might that transformation look like? Well, let's think of this as a two-step process, because there are really two different things that we need to do. We need to shift our coordinate system so that the origin is at 0, 0 instead of its current position at a latitude of 34.11 and a longitude of negative 92.082. Note that there is a negative in there since our longitude right now is in degrees west. And then we'll also need to rotate our coordinate system. Alright, so let's do this in two steps by first naming another coordinate system that we'll just call XY for now. It'll be pretty simple to define a coordinate transformation that goes from latitude, longitude to our new XY coordinate, so let's do that first. We can write that x equals negative longitude plus 92.082. Notice that the negative is in there because here in the US our longitudes are all in degrees west, which of course is why higher values of longitude are on the left and lower values of longitude are on the right. Next we can define that y equals latitude minus 34.11. Alright, so we've defined a coordinate transformation that will map our latitude-longitude coordinate system onto our xy coordinate system. Let's take an example. If we plug in a latitude of 34.16 and a longitude of 92.07, we'll get x equals negative 92.07 plus 92.082 equals 0.012, and y equals 34.16 minus 34.11 equals 0.05. So we find that that point plots up right along the road. We could try another latitude-longitude pair. This time let's try a latitude of 34.17 and a longitude of 92.09. We'll calculate that y equals negative 92.09 plus 92.082 equals negative 0.008, and x equals 34.17 minus 34.11 equals 0.06. So we see that this point is actually at a negative x in our xy coordinate system. Alright, next let's discuss how we get from the xy coordinate system to the UA coordinate system. Obviously, from looking at this, we can see that really what we need to do to get from the xy coordinate system to the UA coordinate system is to simply rotate our coordinate system. We're not moving it up, down, or side to side this time. We're also not stretching it at all. We're just rotating it. So how do we do that? Well, let's start by defining an angle that we have to rotate our axes by. We'll call that angle theta because we like to name angles theta. Since we are dealing with rotation about an angle, it's a good bet that we'll be using our trigonometric functions. Alright, so let's think about how we might do this. We'll start by focusing on that orange point that we chose a minute ago. Let's draw a line from the origin to that point. That line starts at the origin in both of our coordinate systems, and it has the same length in both of our coordinate systems, but it has a different angle relative to the axes. Hopefully this reminds you of a coordinate system that we just learned about, polar coordinates. So let's get sneaky, and let's think about transforming from our xy coordinates to polar coordinates. To calculate our point's position in polar coordinates, we need the radius and we also need the angle of our line with respect to the x-axis, which we will call sigma x. Then we know that we can write x equals r cosine of sigma x and y equals r sine of sigma x. We learned that from our polar coordinates discussion earlier in the toolbox. But if x equals r cosine of sigma x and y equals r sine of sigma x, then we can also define a new angle that is the angle of our orange line with respect to the x-axis and call this new angle sigma a. Thus we can use the exact same language to state that a equals r cosine sigma a and u equals r sine of sigma a. But of course sigma a is clearly equal to sigma x minus theta, so we can replace that in our equation. Now we just need to play around with some trigonometric functions. I haven't subjected you to all the different theorems associated with trig functions, but one important one that we can use at this moment is the relationship between cosines and sines of the differences between two angles. You can always look these theorems of trig functions up if you want to, and you can also look up their derivations, so I'm just going to tell them to you now. The cosine of sigma x minus theta equals the cosine of sigma x times the cosine of theta plus the sine of sigma x times the sine of theta. And the sine of sigma x minus theta equals the sine of sigma x times the cosine of theta minus the cosine of sigma x times the sine of theta. We can now plug these equations into our equations for a and u, and we find that a equals r cosine of sigma x cosine theta plus r sine of sigma x sine of theta, and u equals r sine of sigma x cosine theta minus r cosine sigma x sine of theta. But if we look closely at this equation, we can see that r cosine sigma x is equal to x, and so we can substitute that into both equations, and y equals r sine of sigma x, so we can substitute that into both equations. We now have some fairly simple equations that relate u to both x and y. A equals x cosine theta plus y sine theta, and u equals y cosine theta minus x sine theta. Let me clean all of this up so we can clearly look at these important equations. We see that A equals x cosine theta plus y sine theta, and u equals y cosine theta plus x sine theta. We can actually rewrite this as a matrix equation. Hopefully you can work through and see for yourself that this matrix equation is exactly equivalent to the two equations written above it. We refer to the matrix of sines and cosines as the matrix transformation for rotation of coordinate systems in 2 dimensions. This is an incredibly useful equation. It can actually be used to define any rotational transformations of coordinate systems. This is actually how your computer will rotate pictures if you took a picture slightly crooked and need to correct it, or if you need to rotate a picture 90 degrees to convert from landscape to portrait orientation. Since this rotational matrix is so important, let's take a moment to see how this equation would work for a couple simple examples of theta, examples for which we know intuitively what the answer should be. First, what if we had an angle of theta equals 0? If we were rotating our coordinate systems by an angle of 0 degrees, we're not actually doing anything to it at all. So A should just be equal to x, and u should be equal to y. So let's plug in some values and see if that's what we get. The cosine of 0 is 1, and the sine of 0 is 0. So if we plug in those values, we can see that our transformation matrix is simply the identity matrix. So it is going to tell us that A equals x plus 0y, and u equals negative 0 x plus y. So A equals x and u equals y. That's what we expected, so that makes sense. Next, let's see what happens if we define that x equals 90 degrees or pi over 2. That's going to rotate our axes a quarter of the way around. So if we had a value of x equals 1, we'll now have y equals 1. And if we had y equals 1, we'll now have x equals negative 1. Well, let's do our calculations to see if it works out. We know that sine of pi over 2 equals 1, and cosine of pi over 2 equals 0. So if we plug that in, we see that we now have a matrix of 0, 1, negative 1, 0. So that tells us that A now equals 0 times x plus 1 times y, so A equals y, and u equals negative 1 times x plus 0 times y, so u equals negative y. That actually checks out with what we expected. Our new A is our old y, and our new u is negative our old x. Alright, we've now defined that transformation from xy to au that we wanted. Let's put it into our arrows and look at all of our transformations. So we have one transformation that takes us from lat ln to xy, and another that takes us from xy to au. That's great, but we actually want one transformation that will take us all the way from lat ln to au, so let's rewrite all of these transformations as functions. We'll call our transformation from lat ln to xy the function f, and we can write that xy equals f of lat ln, which equals negative ln comma lat plus 92.082, comma negative 34.11. Next, we want to define a transformation from xy to au. We'll call it g, and we will write that au equals g of xy, which equals cosine theta sine theta, negative sine theta cosine theta, times xy. Then we can write that the transformation from the lat ln coordinate system to the au coordinate system should be defined as au equals g of f of lat ln. Alright, next let's clear out some space and actually compute what g of f of lat ln is. First, we substitute in for f of lat ln and write that g of f of lat ln equals g of negative ln lat plus 92.082, 34.11. Then we can plug in our equation for g, and we find that g of f of lat ln equals cosine theta sine theta, negative sine theta cosine theta, times negative ln lat plus 92.082, negative 34.11. And finally, we can rearrange just a little bit to get a nice equation for computing g of f of lat ln. And remember that au equals g of f of lat ln. So if we want to transform our latitude, longitude data into our new coordinate system that will have our map rotated by an angle theta, all we need to do is choose an angle to rotate over. 35 degrees will probably be good in this case, and when we apply our equation to calculate a and u from latitude and longitude, we rotate our map to get a nice up and down map that will fit well on a printed sheet of paper. Keep in mind that the reason this works is that in computer language, all of those lines, including the river, our topographic lines, the roads and trails, and the locations of the visitor center and campgrounds, are all stored as vectors of latitude and longitude. So when we apply these equations, we convert the latitude and longitude into a new coordinate system, A and U, and we tell the computer to plot all of our points at specific A and U locations instead of at the corresponding latitude and longitude locations. Alright, let's remember all the steps that we've taken to get here. First, this was all possible because we got latitude and longitude values for everything we wanted to plot on the map. Next, we performed what's known as a translation using the function that we've called f here. Our translation took the bottom left corner of the map and moved it from a latitude-longitude location of latitude equals 34.11 and longitude equals 92.082 west to an xy location of 0, 0. This is important because our rotational matrix rotates around the origin. After translating all of the latitude and longitude data, we applied our rotational transformation matrix. That rotational transformation matrix is really useful because it allows us to rotate any data, or really any picture, by whatever angle we choose. After applying our rotational transformation matrix, we now have all of our data in the AU coordinate system, and we simply plot it in this coordinate system. That's it for this toolbox. We've covered transformation among different types of two-dimensional coordinate systems, including Cartesian coordinates and polar coordinates, and we've also computed translations and rotations in Cartesian coordinates. Along the way, we had to use our trigonometric functions and also compute functions of functions, so it's important that you remember these concepts from previous toolboxes. If you don't remember the details of trig functions or functions of functions, please go back and review those toolboxes. In our next toolbox, we're going to talk about spherical coordinates. Spherical coordinates are really important because we actually use them all the time when we discuss latitude and longitude. In this toolbox, we approximated latitude-longitude coordinates as being similar to Cartesian coordinates, and that was okay because we were working over a very small spatial scale. If we were talking about larger spatial scales, like the scale of a continent or an ocean basin, we would really need to put thought into spherical coordinates before plotting something, and we'll get to those details in our next toolbox. For now, don't forget to take the mini quiz on Canvas before class.